All right, so let's go ahead and begin today. So today's class is on doing loops in assembly language. So when I asked my 8 to 11 class if they had heard of loops before in a programming class, they said yes. So were they telling me the truth? So you've done loops like, I guess, in Python or whatever language you learned in your intro to programming? Okay, so you probably have a basic idea of what loops are. It's just when you're doing repeated instruction, until a particular condition is met, right? And then it takes you out of the loop. So I'm just going to show you some examples where we use assembly language to do loops. And then the next assignment, software number 3, you have a problem where you need to use a loop in order to solve that problem. And just like I've been doing in previous software classes, I'll do one of the parts of that assignment, and then I'll have you do the other part. Okay, and again, Thursday assignment to do on Monday of the following week, and tomorrow you have your reg file that we talked about on Tuesday. Okay. Also, just a reminder, this is no different than what's on Canvas, so I'm just giving you a heads up. The midterm, it's a week from next Tuesday, so it's not next week, but it's the week after that Tuesday. It's Valentine's Day, February 14th. Easy to remember. Okay. And I'll make some comments about the test once we're done with the lecture. Okay. All right. So, like I said, we're just going to look at some examples of doing loops in assembly. So here's the first example. This is actually you might have heard the term a for loop. Anyone heard that term before? Some solutions. And as you can see in the flow chart, we're going to set an integer equal to 0. And then we're going to make a decision based on the value of that integer. If it's less than 10, we're going to do some repeated instructions. And then after we do the repeated instructions, we're going to increment I, which stands for integer by 1, and then go back, evaluate again, and keep doing the repeated instructions until this becomes false and then it becomes out of the loop. Okay. So to do this in assembly, the first thing is you have to put your integer and also the number that you're making your decision on. You've got to put those into registers. Okay, and also you should never assume a register is 0. Now, remember last class, if you made sure that register 0 was always 0 by initializing it to 0 as well as all the other registers, and then never writing to register 0, right? You keep it 0. Well, you could make an argument since you initialized everything to 0 that perhaps you didn't need this. But it's a good practice to always make a register 0, even if there's a good chance it's already 0, because that way you get in the habit where if you write a program for a piece of hardware that you didn't design, right? So maybe that piece of hardware, the registers weren't all initialized to 0. Well, then you'll still be safe. Okay. So even though if you had initialized all the registers in the reg file to 0, this wouldn't be necessary. It's still a good practice to always do that. Okay, so that's what we're doing here is we're just initializing a register that we're going to use as a counter to 0. Okay, so when I put counter here, I'm just talking about a register that we're going to use as a counter. I'm not talking about like a counter circuit, like a program counter that you did earlier. Okay, then we're also going to put, the number that we're going to make our decision on. We call this a max count. We're also going to put that into a register. Okay, so that's what this load immediate does. Okay, we're just putting this, and I'll call it a max count. into a register. Okay, and then we're going to use the branch statement. Use branch statements last week. So loops are just an extension of branch statements, where here we're comparing the contents, right, of register 5 to the contents of register 6. So we're evaluating to see whether the contents of register 5 are greater than or equal to what's in 6. And I have my count value, so starting at 0, I got my max count value here. So if x5 is less than x6, we're going to do the repeated instructions. But if these two are equal, well, I'm done and I'm out of the room. So it's just that once you repeat the instructions, you increment your counter by 1, and reevaluate. Right? So this is this one keep cycling until it knocks us out of the loop. Okay. I got a question. Your hand was thrown in. Now, this bit of code here. Oh, I should have said at the very beginning. These are two separate programs. Okay, so here's a program, and they both do the same thing. Do you see what's different though between the two? Here our counter starts at what? 0, and we're counting up, right, until we reach 10. That's when we get out of the loop, right? So you see here we're counting. What are we doing here? Yeah, counting down, right? So we're just initializing this register to 10, and every time we go through the loop, we're decrementing by 1, and then we're doing a comparison here, right, to see if the contents of register 5 are equal to 0, right? Not equal to 0, just keep repeating. Once it equals 0, then we're out of the loop. So this is just doing the same thing, but it's counting down. And if you look at the number of instructions, now assuming that the repeated part are the same number of instructions, if you look at the number of instructions we have other than the repeated instructions, well, we got one less here. Okay, so, typically in this type of for loop, when you're counting down, it can be more efficient, right? Because you're not using as many instructions. Now, an argument can be made that, in most cases, probably just one added instruction, because you'll see that equates to maybe an additional, 40 nanoseconds, isn't that big of a deal. And in this class, except for the assignment you're going to do today, we don't grade you on how efficient you are. If you write an assembly language program and you're using more instructions than what's necessary, you won't be marked down for that. But there is one exception to that I'll talk about when we get to the part of software number 3 that you're going to start today. Okay. Okay. So any questions up to this point? All right. Let's look at this example here. This is actually called a while loop. And you can see here from the flow chart that we come right into a decision point. And as I mentioned before, but just to make sure everyone understands, this X5 is referring to the contents of register 5. X6 is the contents of register 6. Right? So we're just comparing the contents of two registers. If 5 contents less than 6, we're going to do repeated instruction. But if not, if this is not true, well, then we're out of the loop. So this would be the assembly code that you would need for this type of loop, for this flow chart. You can see we're using a branch if greater than or equal to. Right? So it's looking to see whether contents of register 5 are greater than or equal to the contents of register 6. If that's true, it goes into the loop. Does the repeated instructions, and it'll just stay in there until this is true. Once this is true, it knocks us out of the loop. And there can be some additional code here, or you could just end it. You know, if this is the end of the program, you could end it with a trap, you know, the J to done like we saw before, where it just stays on the same line. Now this is very similar. In fact, this is called a do while. And the only difference between the two, as you can see, is just the order of where the decision is and where the repeated instructions are. Here you come right into the repeated instruction, then you do the decision, right? If it's not true, of course, you come back up here, or in this case, if it's true, you come back up here, repeat the loop. And if it's not true, it takes you out of it. So you might have learned this in your first programming class, but the only difference between these two is that a do while loop, you'll do these repeated instructions at least once. Where here it's possible in a while loop that you never get to this point, right? Because this decision point was false to begin with, you would never get to repeated instructions.
So the difference is pretty clear.
Yeah, it's just, you know, here, yeah, here you could break off before you even get here, right?
Yeah.
But here you got to go through here at least once. Let's see. Yeah, and here's the code here. We're using a branch less than. Okay, so if this is true, we're staying in the loop, right? Not true, kicks us out of it. So any questions? This is familiar, right? Because you've done loops before. What's not familiar, or what you haven't done before, is just seen the, you know, the assembly language code, right? See, that's why I was surprised when we were talking about flowcharts at the very beginning of the quarter. See, that's why I was surprised that in a first programming class, you didn't see flowcharts. And I talked to the 8 to 11 students, and they were telling me, I guess, in your intro programming class, instead of flowcharts, they use like pseudocode. Is that what they do? Oh, okay. See, I don't know much about pseudocode. I know what the term means, but I never used it.
Pseudocode is exactly what you're doing there, where it's like, right, it's like start here, do this, then it's like go back here.
So it's using like just like English words for what you're going to write.
Pretty much.
So it's more of a verbal instead of a pictorial. No, it's just that. Well, and I guess it's the same with pseudocode too. It's just, you know, the reason I like a flow chart is once you have a flow chart, it's the same no matter what language you're writing. You know, it's the same, you know, because it's just showing the thought process. So, and I suppose that would be same for pseudocode if it's just writing it out in English. I don't know. I guess I'm more a visual pictorial type of person. I would still prefer flow charts, but maybe it's just because that's the way I learned originally. So a lot of times that's true, right? Whatever you learn, you like the most. Okay, so let's turn the camera. Yeah, so it's going to be a short lecture today. So let's talk about software assignment number 3. Like I said, I'm going to do the second part of it, and then you'll do the first part of it. So here's part 2 of software number 3. First, we're going to read in a 32-bit value from the switches. I forgot to put the 0x here and indicate this is a hex address. Same address you've been using for the switches in previous problems. And then we're going to cause a delay of a half a second. And after that delay, just output that data from the switches to the 7-segment display. And just like you saw before, the 7-segment display, its address is 40 hex from where the switches are at, okay, the address of the switches are. Now, in order to do this problem, there's some additional information that you need, okay, that we're going to figure out here. Okay, the first thing is, from your CP133 class, do you remember well, I actually wrote it up there. I didn't need to have that up there, but yeah, if you recall, from the CP133 class, the frequency is 100 megahertz. Okay, now, Do you remember how to get period of a signal from its frequency? Right, it's just reciprocal, right? So what's the reciprocal of 100 megahertz? It's actually smaller than that. It's smaller than microsecond.
10 nanoseconds.
Yeah, it's actually 10 nanoseconds. You know, in Vivado, when you're running a simulation and you put the pound sign, the number sign, and then a number, that number sign tells the software that the number is in nanoseconds. That's why, you know, you see number sign and, you know, before all your test cases, because it's putting a 10 nanosecond delay for all your test cases. Now, the Otter, as you're going to find out, I think I mentioned this earlier, but we'll talk more about it in a few weeks. But the Otter is going to run at 50 megahertz. Yeah, you'll see that when we get towards the end of the quarter, this won't be till after the midterm, you'll see that you'll be given a module that Dr. Hummel designed that puts circuitry around the Otter. Okay, like you'll have your working Otter, you know, CPU, MCU, whatever you want to call it, right? It'll be all together, hopefully working. And then you'll attach around it. It's just a file that, you know, you'll connect up just like you connect individual modules together that interfaces the Otter to peripherals, you know, like the switches and buttons on your basis board and the LEDs and the 7-segment display. And you could add, you know, I mean, that's what Dr. Hummel designed it for, just those peripherals, but he made it so it's flexible where you can add stuff. So you could add like a keyboard as an input or add a monitor as an output. Okay, you could do that fairly easily. Okay, well, part of that circuitry, it's called the wrapper. Okay, the Otter wrapper. Well, part of that circuitry that surrounds the Otter is a clock divide by. Okay, you might have seen a clock divide by in CP133. And that clock divide by is going to divide the basis board clock by 2 and run the Otter at 50 megahertz. So if 100 megahertz has a 10 nanosecond period, what does a 50 megahertz signal have as a period? It's just going to be twice, right? You have the frequency, it doubles the period. 20 minutes. Okay, so that's what the Otter is going to be running. Now, we will talk about why this is so in a couple of weeks. But most of the Otter instructions, so again, in your assembly language manual that you have, most of those instructions require 2 clock pulses, okay, 2 clock cycles to execute. I put most here because it's not all of them. There's some that require 3 clock pulses, okay, but most of those instructions, in order to be executed by the Otter, requires 2 clock cycles. Excuse me, 2 clock cycles. So that means how much time will it take based on this 20 nanosecond period that the Otter is running at? How long will it take to run an instruction? 40, right, just 40 nanoseconds, right? Because each period, each clock cycle has a time of 20 nanoseconds. So each instruction, again, this isn't exact because not all the instructions are 2 clock cycles, but most of them are. So we're just going to assume for simplicity here that they're all at 2 clock cycles. Well, each instruction would take 40 nanoseconds to execute. So now what we can figure out is we can figure out how many instructions we need to use up a half a second of processing time, because that's really what we mean by a delay here. Is delay the processing or to process half a second before we do anything else. So how could we find how many instructions are in half a second when each instruction takes 40 nanoseconds? Divide what by what?
25 seconds over 40 seconds.
Okay, yeah, because sometimes people get it backwards. But yeah, it's a half a second divided by 40 nanoseconds. And what's nano 10 to the what? Yeah, -9. Does anyone have a calculator who can do that? It's gonna be a big number, right? Yeah, that sounds right. Yeah, 12.5 million. Right, so the otter, in half a second, is executing that many instructions. Okay, now you'll see how that comes into play when we write the code to actually create this delay. Okay, but that's how you do the calculation.
Why do we want the delay?
Oh, great question. In fact, I'm working on this right now. and in preparing for what you have to do, or what you may have to do for your final project, which most people do. I'm actually working on this, and right now I'm stumped. So hopefully I'll have it figured out by the time you guys get to it. But where it comes into play is, let's say you're doing a final project, you know, like you got your auto working and everything, and now you're writing a program where you want to input data from the switches, and you know, you want to input more than one switch data, right? Like you want to set the switches, use that as input data, then at a later time, you know, have different data on the switches and then use that, right? Well, if you don't have a delay, wherever you have a load instruction, like loading from your switches in your program, it's going to be trying to load the switches like in nanoseconds. Right, and there's not enough time. Right? We're not that fast, right? Nobody's that fast. So you'll need a delay like this so that it allows the user time to make changes to the data. So, yeah, right now, you know, my otter's working, and I'm sure it's working because Dr. Hummel, I might have mentioned this in another class, but it's really amazing. So it deserves to be said many times. He made this test file, you know, this mem file. And, you know, I don't like looking on a screen, especially when something's really long. I print it out. I know it's a waste of paper. I'm sorry, but I'm just old school. I get headaches when I look at a computer screen too long. So I like hard copies of stuff. That's why I did this. But anyway, I printed out. I mean, it's like this thick, and it's just code, you know, it's just assembly line, and it tests every instruction, you know, and he put that together. And I mean, it's impressive. It's really impressive, but it checks every instruction. Now, when you run it on your board, it only takes like 1/3 of a millisecond to run through all of it. But you know, it's a lot of instructions. But anyway, that's how you test out to make sure that your otter's working right on the board. And then I wrote a very simple program where, you know, you need to change the switches successfully. So I needed the delay, and it works fine in RARs. I even made a mem file of that simple program and put it in Vivado, and I simulated it, and it works in the simulator. But for some reason, it will only take the first switch data I give it and give the correct result, but it won't take any subsequent. So I don't know if it's somehow getting in an infinite loop, or I don't know. It's really weird. So anyway, hopefully I'll have it figured out. And when I do, I'll let you know. But right now I'm puzzled by it. But anyway, that's where it comes into play is you need to give the user time to change like input data. So the program has to kind of wait. All right, so let's see what the code would be for this. And like always, we start with the flow chart. So let me get my flow chart out. Okay, so remember, in a flow chart, you always start with start. And then what are we gonna do next? Well, I guess it's the first thing, right? The start is just beginning, right? But what's the first thing we need to do here? Yeah, read from the switches, right? So remember, in a flow chart, we use the parallelogram symbol for reading input data. So read switches. Okay, then the next thing I have in my flow chart, and remember, a flow chart doesn't have to be, every instruction, right? Now, in most of the programs we've been doing here, we don't have many instructions to begin with. But, like when you do your final project and maybe you'll have, a lengthy program, you don't need a flow chart, like where every block is an instruction, right? It's more, logically what's going on kind of thing. But what I put for the next one after reading the switches is I put, what we were doing over here, initializing the registers. Initialize counter. And, the max count. Okay, then I'm gonna increment by 1 before we go into the loop. Okay, I'm gonna make a decision here. Okay, check. It's not equal to max. Okay, and if we're not equal to the max, we're gonna come back and increment the counter by 1. So this is true, it's not equal. And if false, we're just gonna output to the 7-seg display. This is output. And we just end it. Okay, so that's basically the flow chart that we need to do for this. So the assembly code. First thing I did, well, what has been the first thing you have been doing anytime you've had to input data from a switch? Yeah, you do a load immediate where, what are you loading? Address. The address of the switch address. I did that first. Load immediate. I use register 6 for the switch address. Okay. Then, I could do a load word next, but I decided to initialize my counter, and I'm going to use register 8. And remember, you can use any of the registers X5 through X31. So I'm just picking these registers, without any thought at all. Okay, so this is initializing counter register. I'll call it. Okay, then I load the data from the switches. The load word, since it's 32 bits, right? We're using load word. And I'm going to put the switch data into register 5. Okay, and you remember in this instruction, the way it works is it takes this number out front, it adds it to what's here, which is our switch address, and then it uses that as an address and takes the data at that address and puts it in this register, right? So you're all familiar now with this offset and its use, because its use is when we go to output, all we have to do with our store word is just put a hex 40 here, right? And it will take us to the 7-segment display address. Okay, then I have to put my max count, right? What I want to count to in the loop. I got to put that in a register, just like we did for the for loop over there, right? We put 10. Well, here, okay, I'm going to use register 7. Okay, I'm going to leave this blank for the moment, okay? Because we're going to put a number here. But to understand what number goes here, we have to do a little bit more, okay? So I'm coming back to this in just a little bit. Okay, so now we're going to go into our loop. Here's my label loop. And the first instruction in the repeated part of the loop is an add I, where I'm incrementing the counter. Okay, then after this add I, I'm gonna do a check where I'm gonna use a branch not equal to of this number that I haven't told you yet. And my new count value after I increment by 1. So if my counter is not equal to this number that I'm gonna give you in just a moment, I'm just gonna keep looping, right? But once these two numbers become equal, I'm gonna fall out of the loop. And I'm just going to output the switch data to the 7-segment display. So again, when you output, right, in assembly language, it's a store command. Here it's a store word. And then that's where we use the hex 40 offset for the switch address that we already have here in register 6. Okay. So before I tell you what number has to go here, does all of this seem good? Okay. Well, what number goes here is determined by how many instructions we have in this. See, we just have these 2 instructions in the loop. And each instruction is 40 nanoseconds. And just a little while ago, you told me that, for one instruction, right, one instruction is 40 nanoseconds. And if we have one instruction, we would need this many, 12.5 million instructions, like single instructions, to get a half a second delay. But see here, I have 2 instructions in my loop, right? Because this is just going to keep going like this, right, until the condition is met and we follow the loop. So the number I put here is not this, but what? Yeah, half of it. Yeah, half. So yeah, it'd be 6.25. Right, because it'll be in this loop that many times, and the loop has 2 instructions. So 80 nanoseconds times this is half a second. Now, someone else or someone in the previous class mentioned, oh, well, what about these instructions, right? Because they have delays too, right? They're each going to take 40 nanoseconds. But when you compare, let's see, 40 nanoseconds, 40, what's that? 160 nanoseconds to half a second. You know how many nanoseconds are in half a second? A lot more than 160. So, I mean, it's not going to matter much, right? I mean, I guess if you want to be super precise, you could, make this 6,249,998, whatever it is. This is good enough, right? Especially in the case we're talking about, like with the user with the switches, you're not going to notice the difference, right? Of 160 nanoseconds. Okay. So any questions on this? Like I said, you may very well have to do something like this for your final project. Okay, now your assignment, the one that you're going to work on, which is part 1 of this. Okay, so let's look at that. Part 1 of software assignment 3. It says, read a 32-bit value from the switches at address 11, all zeros. Assume the 32-bit value is a combination of 2 16-bit unsigned values. So split the 32-bit input into 2 16-bit values, an upper and a lower, right? Because remember, at each address you have 32 bits, but you're just going to split it and consider the lower 16 bits a number, the upper 16 bits a number. And then take those 2 16-bit numbers that you're treating as unsigned and multiply them together. And then output the result to the 7-seg at address 11000040. Okay. Now, this is where the efficiency part comes up. Remember, I said everywhere else in this class, you don't have to worry about efficiency. If you use more instructions than what you need, that's fine. But here I do want you to consider efficiency in this sense. Let's say one of the numbers is 40,000 and the other number is 2. How can you code it so it's more efficient, because one way of doing, well, actually, before I ask you that question, I should have asked you, how can we do multiplication when we don't have a multiply command? Right? Our instruction set, we don't have a multiply command. So how are we going to do multiplication?
Addition, a bunch of columns.
Yeah, successive addition. All right. So that's where the loop comes in. Okay. So now I'll ask my question again. How can we, make our code more efficient? Because let's say one number is 40,000 and the other number is 2.
Just add 40,000 twice.
Yeah, you'd want to add 40,000 twice, not add 40,000 times. Right? Because, if we add 40,000 twice, we're just doing a loop twice, as opposed to add 40,000 times, we'd be doing a loop 40,000 times, right? Which is a lot more processing time. Okay. So that's the added thing that's not here that I want you to do. Okay. Does that make sense? All right, last thing, and then you can get started, is I just want to make a few comments about the midterm. Like I said at the beginning of the class, and again, I didn't change anything. It's what's on Canvas. The midterm is on Valentine's Day, okay, which again is a week from Tuesday of next week. Oh, it's not next week, it's the week after. And it's a 60-minute test. And for this class, it starts at 12:10, so we don't have to be here late. In fact, you have to take it in roll section. You can't take it at 8:10, even if you wanted to. Okay, you got to take it during this time, and it's going to be 60 questions, and it's all multiple choice, true, false. There's no problems. Okay. And you want to make sure you get here on time, because in this class, most people have been really well with attendance and also being on time. But if you've had trouble getting to class at 12:10, don't have trouble that day, because if you come in late, you lose the time and you'll have to complete it in, a shorter amount of time. Now, I didn't put it up here, but the material will go from, our first lecture all the way through next week. Okay, next week is both lectures next week are hardware. Okay, there's no software next week. Monday, you'll build the ALU and the immediate generator. And a week from today, you'll build the branch condition generator and the branch address generator. Now that may sound like a lot, okay, but actually the program counter and the reg file are probably the two that involve the most code. And I think the reg file probably involves the most thinking, because you got to get used to that syntax, for the RAM, and also about not writing to the zero register, right, to keep the content 0. You'll see next week that the ALU is one big mux. So you're just going to have one case statement for the mux. And you've done plenty of case statements, so I don't think that will be too much trouble. And then the immediate generator, you can do in 5 assigned statements. It's just 5 assigned statements. Okay, and you'll need to use things that you learned in 133, like concatenation. Does anyone remember that word, concatenation, from 133? What was concatenation?
In this context,
Yeah, it's like joining bits together, right? Like you can take 5 bits of this thing and 3 bits of this thing and put them together. So when you do the immediate generator, you got to do some concatenation. There's also replication, which is very similar. So yeah, there's not that much really to those two. And then the branch modules, the condition generator and the address generator. The condition generator is one if statement. It's like one if, maybe a couple of if else's, and that's it. And then the branch condition address generator is like 3 assigned statements. Okay, so even though like you're doing 2 modules both days next week, each module is really not that much. Okay. So anyway, the material for the midterm does go through the end of next week. And again, it starts at the beginning. Now, guessing is discouraged. Okay, like I have up there, guessing can be detrimental. Because for every correct answer, you get a +1. For every blank answer, it's -1. For an incorrect answer, it's -1.5. Okay, so if there's a question that you have no idea what the answer is, right? You look at the choices, it's multiple choice, but like, you have no idea. I would say unless you're one of those people that like always win a raffle or always win, how there's some people like that. It seems like it's the same person that always wins like the lottery or the raffle, like the lottery. It's always like somebody in their 80s, usually. Doesn't it seem like it's older people? I don't know if that's like a conspiracy or something, right? Because they don't have to pay the annuity as long, right? No, that's not true. It goes to a family member. But anyway, unless you're a person like that, you probably shouldn't answer. If you're a person like me who's never won anything in their entire life, then you probably shouldn't put an answer if you absolutely, like I said, don't know what it is. If you're sure, of course, that's +1, right? If you're not so sure, then it's really your level of risk tolerance, right? Whether you're like a CD person when you invest, or whether you're like a mutual funds person, and ride the stock market, that kind of thing. So you have to make that choice if that situation arises. But I would think, let me just finish and I'll answer your question. But I would say, now I can't guarantee anything, okay? But I would say, someone that's been coming to class, that's, been doing the work, doing the work conscientiously, like they've been doing their own thing. They're not relying on the other person. And, I would say someone in that position shouldn't be stressed out by this. But don't get me wrong, you got to prepare. Never come into a test, not prepared, right? Don't go into a test cold. Now, I have my videos on Canvas. As you know, I've been recording these lectures, so you can go back and review if you need to what I said in class. Also, I don't know if you've noticed, but on Canvas where I put the video, I have the outline of my notes. In fact, what I have on Canvas is more detailed than the notes I use in class. So you can definitely go back and look at what was talked about and review. Yeah.
Yeah, so for the points of this one, it's to clarify. So you say a blank is -1 and a correct answer is +1, but does that mean if I get a correct answer and I leave something blank, it zeroes out to 0? Or does it mean that the total, like if I leave a blank, then I just don't get credit?
That's a good question. I mean, I haven't really thought about that yet. I mean, I could, like something I might, is that, let's say there's one question that just about everybody needs blank. I could like X that out. I could not count it for everything. My initial thought was what you said first, that if like say there's 60 questions, then a person had 30 correct answers and 30 blanks, that would come out to just a 0, right? A null. But it wouldn't be a 0% because it would be matched against how other people did. So, if a 0 meaning that 30 were correct and 30 weren't answered was like the high score, that would be like 100%. That make sense? Yeah.
Could you get a negative or a negative?
Yeah, it's possible, right? Because if you had, like, say you had like 45 incorrect and you left everything else blank, that would be a negative.
Yeah.
But it wouldn't necessarily be a failing grade. Now, I mean, I would hope that there wouldn't be a person that would have 45 incorrect.
Everyone's still has
Well, I mean, if everybody were to submit a blank test, I would just give another test. Not on the same day. I'm guessing that most people are going to be able to answer most of them, I would think. I don't know, maybe I'm wrong, and if that happens, we'll cross that bridge when we get to it.
I guess going back a little bit of thought about the test.
Okay.
So, for example, the instruction for one, you say to optimize your code to size. So in this case, we're going to optimize kind of like class instructions. But
Where did you see that?
just on the in Canvas, the lab man was for question or the scientific question, once it's optimized.
Okay, well, remember, we're not using that, right? The criteria is what I put on Canvas, the software assignment criteria. That's what we're using for all the software assignments. So,
I'm just saying specifically, for this one, right? I think you want less instruction, right?
right, but it doesn't come out, well, not that you want less instructions. It's just like I said earlier, if you have like two numbers, you know, one big, one small, you want to use the small one for how many times you go through the loop, so it's more efficient. That's all I mean. I'm not going to count instructions.
Yeah, what I just want to ask you is that, like, if there's a point where you're being super clever, like, there's a multiplication, this, like, the case you gave was 40,000 times two. You just make it one.
Say that again.
40,000 times two. Big shit is one.
Okay, well, actually, this is a good question. This is a good question. Oh, I'm sorry, is it Toma? Toma's asking, you know, like in the case of 40,000 times two, another way to do it would be to do a shift, right? Because you can do whole number power of two multiplication by doing shift, but you can't do like a times three or, you know, something other than a whole number power of two. So, I mean, if somebody, I mean, I'm not limiting it. What I'm expecting people to do is just do successive addition, okay, because that falls into the loop thing. Now, that's not to say you couldn't do multiplication by a combination of shifting bits and addition, right? Because you could do a times three by shifting one place and then adding the original to that, right? That would give you times three. But I mean, if somebody wants to do something like that, but it'd be more complicated than what successive addition is. Well, for this particular assignment, it wouldn't be expected. But, you know, like for a final project or something, that's something someone could think about doing, you know, if they wanted to. Yeah, but for this assignment, you're just expected to do successive addition using a loop. Any other questions? Okay, so you have the remainder of the time to work on your assignments. Again, the priority should be the reg file if you haven't finished that, because that's due tomorrow. And then the software assignment, which is due Tuesday or Monday of next week.
Yes, just one more time. You say that, like, if we study, if I.
Yeah.
Yeah.
Well, I would think that that's
Still recording.
I mean, celebrity is walking.
Right, yeah. So throwing up signs.
The thing, what's there?
Quick question. Like, conceptually, we understand the difference between loading the words and loading the computer. They're both going to registers. You both using the software. So what's the point of first? It's
How many registers are? Yeah. What is that? Like I always talk about this. And that's the way I thought.
So, no, this time, so we're gonna do, cartoons. Until we realize that both.
Okay, this registered, 32 registered is.
So this says that we can.
That the memory also.
Are you? Oh, we bought it? No, like we had, I've had like back-to-back midterms for like since Tuesday, and so I was like, oh, I'm just gonna use the extra days. Oh, okay, well, yeah, just, I mean, there's. If I remember, I'll do it in class today. You said it's for Harvard Human Science, because like the goes. I can email you. Yeah, yeah, just email me.
Okay.
Do you think you'll have it ready tonight or? I'm gonna bother like this week. I want to have it.
Okay, well, I'll try to.
Oh,
Usually when I get home, I don't feel like.
Yeah, there's understandable.
We'll get at least some questions. Well, they cancel